I'm Colin Walls, and I'm here once again to talk about embedded software. Today I want to talk about a technical problem which besets many real-time developers, which is true of most embedded systems seem to be real-time. Real-time means lots of things. Broadly speaking, a real-time system is one which functions in a predictable fashion. And this requires certain disciplines when it comes to programming. You must avoid anything which is non-deterministic, in other words, anything which is not predictable in the time domain. And also you need to look at failure scenarios, what can go wrong and how you can mitigate against it in order to enable your system to behave in a predictable fashion. Today I want to think about a particular area which is dynamic memory allocation. Now, it's very common practice in the C language to say, right, I need some memory to store something. So we make a call to the malloc function. We tell it how much memory we want, and it returns a pointer to it. And that's great. We then use the memory, and when we've finished using it, we use free to get rid of the memory again. And that's great. It works very well. On a desktop computer particularly, there is essentially no problem at all with using malloc. On a real-time system, you need to think about it a bit more carefully. There are two main areas of concern, one of which is determinism. Malloc is very rarely written in a way which is actually deterministic, so the time taken to allocate a chunk of memory is not predictable. That's a problem. It can be addressed in various ways, but it's essentially one that could easily be a showstopper if you don't have a malloc function designed for a real-time application. The other area of concern is failure handling. Now, why would it fail? Why would malloc fail? It will fail because it hasn't got enough memory to answer your request. So if you ask for more memory than is available in the heap, you'll get an error response. The error response is a return of a null pointer. That's okay because you can predict how much memory you need, perhaps overall, you know how much heap you've got. Why should it run out? Well, the answer is, for example, when you are performing a series of allocations and deallocations in a sort of random kind of order, and the result is fragmentation. Take my example here. We have a heap which is 10k, just a round number. I have made various allocations and deallocations over time, so now I have a layout that looks like this. I've got 3k of free memory, then I've got a 4k chunk which is currently in use, and another 3k chunk which is free. So I've got 6k of free memory. What if I now execute a call to malloc asking for 4k? It will fail. It will fail because there is no contiguous piece of memory which is enough for my requirements. That's fragmentation. It can't be fixed. You can't actually fix this problem because malloc can't do any housekeeping and rearrangement of memory because it's returned pointers to where the data is, and there's no way of updating those pointers later. The only way of approaching this is to completely rethink how malloc works, and instead of using the heap, we use a block memory allocation facility which is common with many real-time operating systems. So we create a pool of memory blocks of various sizes, a number of pools. And a simple way, if you don't know how much memory you're going to need and you just want to make it as flexible as possible, you simply create a number of pools of geometrically increasing sizes, so 6, 32, 64, 128 bytes, and so forth. If you do know how much memory you typically want, you create a pool with that size chunks in it. Now, when you call your modified version of malloc, what it will do is choose the pool which will yield the appropriate size chunk of memory. It may be a bit big, but it will be big enough, certainly will be big enough. There's no chance of fragmentation because we're dealing with the allocation of blocks of memory. In my example here, I've got a series of 4 pools. If I make a call asking for 16 bytes, that's fine, it comes from the 16 byte pool. If I ask for 9 bytes, it comes from the 16 byte pool. So I'm getting a bit of extra memory, but I'll relinquish it in due course. There's no real waste. If I ask for 31 bytes, it comes from the 32 bytes pool. If I ask for 65 bytes, sadly, it comes from the 128 byte pool. So there's a bit of an overhead there. but this is quite manageable and not something which is a big difficulty. The big benefit is the memory allocation mechanism provided by a real-time operating system will typically be deterministic, and the failure mode, there is only one failure mode, and that is you run out of partitions in a particular pool, or blocks in a pool. Now, that is still a failure and you need to keep an eye out for it, but typically we can set it up so the task is suspended pending the availability of that memory. So it's a smooth error handling situation. It needs work on your part to rewrite malloc and make use of these pools. It isn't very difficult, and you may find that your RTest vendor has done it for you already. The most important thing is to be aware that malloc is a pretty dangerous function to use in any kind of system which is described as real time. That's it for today. I hope this is useful. By all means, contact me if you have any queries about this approach, and it's something I'll probably be investigating in more detail on another occasion. But for now, that's the lot, and I'll say bye for now.